Swayam Prabha. Digital India. Educated India.
So, we will continue the topic mathematical modeling. Mathematical modeling. In the last class, we have discussed about the state variables and state equations, and in this class we will develop the mathematical model first for a CSTR, continuously stirred tank reactor. So, we will take CSTR example and we will derive the mathematical model. This is a jacketed CSTR. This is a tank. This is the jacket. Now, one medium is introduced here and that medium is coming out here. First of all, the feed which is entering to the reactor has the flow rate of Fi, concentration of the feed is Cai and temperature is Ti. The suffix I indicates the input, A is the component, I mean Cai is the input concentration of component I, and Ti is the input temperature. Fine. The product stream which is coming out from this CSTR has a flow rate of F, concentration in terms of component A is Ca and temperature is T. Now, before deriving the mathematical model for this CSTR, first we will know the units of different flows, like Fi and F along with the medium, coolant medium flow rate Fc. So, all these flow rates are basically volumetric flow rate. Volumetric flow rate. Here temperature is Tci, outlet flow rate is Fc and outlet coolant temperature is Tc naught. Concentration Ca and inlet concentration Cai both are molar concentration, I mean unit is say mole per unit volume. Fine. Ca and Cai both are molar concentration. For example, they are in mole per unit volume. Next we will consider the assumptions. So, first assumption is perfect mixing. First assumption is perfect mixing. That means the temperature of this outlet stream T and composition Ca, they are same with that of the reaction mixture. Fine. The perfect mixing indicates everywhere in this tank temperature and concentration they are identical, and the outlet temperature and composition also identical with the temperature and concentration of reacting mixture. Second assumption is liquid density rho and the heat capacity Cp, they are constant. Liquid density rho and heat capacity Cp, they are constant. Third assumption is we are considering a simple exothermic first order reaction. This is a simple exothermic first order reaction. Exothermic first order reaction, and to remove this exothermic heat, a coolant stream is introduced in this jacket. This is the coolant stream. To remove the exothermic heat, a coolant stream is introduced in the jacket. Fourth assumption is the reactor is perfectly insulated. The reactor is perfectly insulated. That means there is no heat loss from the reactor to the surroundings. It means no heat loss from the system to the surroundings. Fifth one is coolant is perfectly mixed in the jacket. Coolant is perfectly mixed in the jacket. Fine. And last assumption is we will not consider any energy balance for the jacket. There is no energy balance for the jacket. Fine. These are the assumptions adopted for this CSTR system, and based on these assumptions we will derive the modeling equations. Now first we will go for the overall mass balance. First we will go for overall mass balance. So to develop the overall mass balance of this CSTR system, we need the conservation of mass. What is that? Conservation of mass is rate of mass accumulation equals to rate of mass input minus rate of mass output. This is the conservation of mass. Now for this CSTR system, what is this term? I mean, how we can represent the mass of accumulation? See, in this reactor system, you consider the volume of the liquid is V. The volume of the liquid in the reactor is V. Now, if V is the volume, if we multiply with density, so this whole term becomes mass. Now, differentiation of this is the mass flow rate, fine, d dt V rho, that is the rate of mass accumulation. Now, rate of mass input to the system is basically Fi, but we know that Fi is the volumetric flow rate. So, we have to multiply with rho. So, Fi multiplied by rho, that is the input mass rate. Similarly, what will be the output? Output flow rate, I mean the volumetric flow rate, that is F. So, if we multiply with rho, then this is the output rate. Now, we have assumed that rho and Cp both are constant. If rho is constant, then we can write this rho dV dt equals to Fi rho minus F rho. That means dV dt equals to Fi minus F. Fine. Suppose this is equation number 1. So, this is the mass balance equation. Fine. Similarly, we can go for mass balance of component A, or you can say the component mass balance. So, we will consider in the next mass balance or component mass balance. Component mass balance, and the component is here component A. So, what is the conservation principle for this? Rate of accumulation of component A, this is the accumulation term, then rate of input of component A, then rate of generation, of component A minus rate of output of component A. Fine. This is the conservation principle for component mass balance. Now, we have to derive all these, we have to write all these individual terms: accumulation, input, output and generation. Now, for this CSTR system, what is the accumulation term? Volume multiplied by Ca. Now, if we want to represent in terms of rate, then d dt of Vca. Clear? This is mole per unit time, mole per unit volume Ca, and V is volume. So, mole per unit time overall. So, what is the input? Fi is the flow rate of input stream and concentration is Cai. So, Fi multiplied by Cai, that is the rate of input of component A. Now, what is the generation? Minus Ra into V. See, minus Ra is the rate of disappearance of A. If we multiply with minus sign, then we get the generation. Fine. Minus Ra is the rate of disappearance of A. So, if we multiply with minus, then that becomes generation. And what is the output? Output is F multiplied by concentration of output stream, that is Ca. So, from the conservation principle, we got this equation. Fine. Now, we can write this equation in this form: Ca dV dt plus V dCA dt equals to Fi Cai minus F Ca minus minus of Ra into V. Now, we know the dV dt term. I mean, if we substitute equation 1, then this equation becomes Ca Fi minus F plus V dCA dt equals to Fi Cai minus F Ca minus minus of Ra into V. Now, this F multiplied by Ca and this FCA will be cancelled out. Then we can rearrange this equation to V dCA dt equals to Fi Cai minus Ca minus minus of Ra into V. If we divide again both sides by V, we will finally get dCA dt equals to Fi divided by V Cai minus Ca minus minus of Ra. Minus of Ra is the rate of disappearance of A. Now, if we consider Arrhenius equation, then accordingly we can write minus of Ra equals to K naught exponential of minus of E divided by RT into Ca. According to the Arrhenius principle, the reaction rate equals to pre-exponential factor, then exponential of minus E divided by RT Ca. E is the activation energy and R is the universal gas constant. If we substitute this reaction rate expression here, then finally we get dCA dt equals to Fi divided by V Cai minus Ca minus K naught Ca exponential of minus of E divided by RT. So, this is the final form of component mass balance equation. Fine. So, these two equations we have derived based on the conservation of mass. In the next, we will consider the energy balance equation. Energy balance equation. Energy balance equation for the example CSTR system. What is the conservation principle of energy? Conservation principle we can write in this form: rate of energy accumulation equals to rate of energy input minus rate of energy output minus rate of energy removed by the coolant plus rate of energy added by exothermic reaction. So, here 4 terms are involved: accumulation, input, output, energy removal and energy added by the exothermic reaction. So, next we have to represent all these terms using the mathematical terms, I mean variables. So, what is the energy accumulation? See, volume in the tank is represented by V, fine, and if we multiply with rho, this becomes M, then Cp, then dt. Energy term we can write in terms of M Cp dt, fine. Now, here we are considering reference temperature equals 0. Now, if we write here d dt of V rho Cp T, then this becomes rate of accumulation of energy. Now, next we will consider the rate of energy input. Volumetric flow rate of input steam, that is Fi. If we multiply with rho, then that becomes mass flow rate. Similarly, Cp, then dt, I mean Ti minus T reference. Here reference temperature we are assuming 0. So, Ti, and you recall we have considered the Cp, that is constant. What will be the output, rate of energy output? The flow rate of outlet steam, I mean the volumetric flow rate, that is F. Similarly, if we multiply rho, this becomes mass Cp and outlet temperature is T. Now, rate of energy removed by the coolant, this one, this will represent by Q. Energy removed by the coolant is represented by here Q. What is Q? How we can calculate Q? We know flow rate Fc, rho C, Cpc, and then temperature difference is outlet temperature of coolant minus inlet temperature of coolant, fine. What is the last term? I mean, how we can represent the last term? Last term we have to consider in this way: minus del H. that is heat of reaction, then minus RA multiplied by V. Minus del H is here heat of reaction. It is well known to us that heat of reaction is negative. I mean, this negative term is used for the case of exothermic reaction, and for endothermic reaction we use here positive sign. So, this term represents the energy added by exothermic reaction. Next, we need to simplify this equation. Now, dividing both sides by rho Cp, V d capital T d small t plus temperature dV dt equals to Fi Ti. Since we are dividing both sides by rho Cp, next term is F multiplied by T, then Q divided by rho Cp, and finally minus del H minus Ra V divided by rho Cp. Now, we will substitute this term dV dt. We have the equation of dV dt obtained from the total mass balance. If we substitute dV dt, then we can write it like this way: T multiplied by Fi minus F equals to Fi Ti minus Ft minus Q divided by rho Cp plus minus of del H minus of Ra into V divided by rho Cp. Now, this Ft and this Ft we can cancel, and then we get V dt dt equals to Fi Ti minus T minus Q divided by rho Cp plus minus of del H minus of Ra into V divided by rho Cp. And finally, we will divide both sides by this volume term. Then we get dt dt equals to Fi divided by V Ti minus T minus Q divided by V rho Cp plus minus of del H minus of Ra divided by rho Cp. Now, again we will substitute here the Arrhenius law. Then dt dt equals to Fi divided by V Ti minus T minus Q divided by V rho Cp plus minus of del H cannot Ca exponential of minus E divided by RT whole divided by rho C. So, this is the energy balance equation. This is the energy balance equation. So, for the example CSTL system, we got three equations. One is based on total mass balance, then component mass balance, and last one is based on energy balance. Now, the modeling equations I am writing here, one we got dV dt, that is equals to Fi minus F. Second equation dCA dt, that we got Fi divided by V, CAI minus CA minus K naught CA exponential of minus E divided by RT, and energy balance equation we got, that is dt dt equals to Fi by V into Ti minus T minus Q divided by V rho Cp plus minus of del H Ca K naught exponential of minus E divided by RT whole divided by rho Cp. Fine. Here I have mentioned that Q equals to our coolant flow rate is Fc. Now, density is suppose rho c, heat capacity if we consider Cpc multiplied by the temperature difference. What is the outlet temperature of this? TCO minus TCI. So, this is the expression for Q. Now, we will just classify, we will just see what are the different variables involved in the modeling equations. Here, what are the input variables? Input variables are CAI, then Fi, then Ti, then Q. We are not considering FCTCI, we are considering Q, and F. Definitely F will be input variable if this is considered as the manipulated variable for controlling the liquid height or liquid volume. So, these are the input variables. What are the output variables? Output variables are here V, Ca and T. See, in these three modeling equations, V, Ca and T, they are present within the accumulation term. So, these three variables are also state variables. So, we can write here these are also state variables because they are present within the accumulation term. Now, among these input variables, which are the manipulated variables? For the example CSTR system, if we consider liquid volume is the first, one control variable, and another one is say temperature. Fine. Now, the corresponding manipulated variables are, if we consider F as the manipulated variable for V and Q as the manipulated variable for temperature, then what are the, so Q and F, these two are basically manipulated variables. Fine. So, these three, the rest input variables are load variable or disturbance variables. Fine. Among these 5 input variables, 2 are the manipulated variables and other 3 are the load variables. So, this is the development of model structure for the sample CS tier, and we have seen the different variables which are involved in this example CS tier. Before going to discuss another system, we will study about the degrees of freedom analysis. So, we will next study the degrees of freedom. Degrees of freedom. So far we have discussed about the modeling of chemical processes. After deriving the mathematical model of a process, we need to solve those modeling equations. The solution of a model structure is basically called simulation. Fine. We need to simulate the modeling equations. Now, for the simulation of a modeling equation, we need to describe these degrees of freedom. Degrees of freedom, which suppose is represented by F, then we can write F equals to V minus E. Degrees of freedom we are representing here by F. Then F equals to V minus E. V is the total number of independent variables. Total number of independent process variables. And E is the total number of independent equations. Fine. So, degrees of freedom basically total number of variables, independent variables minus total number of equations. Now, in the analysis of degrees of freedom, we will consider three different cases. In the first case, we will consider, say, F equals to 0. It means number of independent variables equals to number of independent equations. That means the system is exactly specified. When degrees of freedom equals 0, then we can write V equals to E. That means number of independent process variables equals the number of independent equations. In this situation, we can say the system is exactly specified. I mean, there is no problem to find the solution of the modeling equations. In the second case, we will consider F is greater than 0. That means V is greater than E. Fine. So, in this case, the system is called under specified. How we can make it exactly specified system? By the inclusion of F number of additional equations. So, to make it exactly specified, we need F additional equations. To make the underspecified system exactly specified, we need F number of additional equations. Then we can only get the solution of the modeling equations. Last case is F is less than 0. That means total number of independent process variables is less than total number of independent equations. and in this case the system is called over specified. Fine. So, to make this over specified system exactly specified, we need to remove f number of equations. So, to make the over specified system exactly specified, we need to remove f number of equations. Usually in practice, the case 2 is the common. I mean, f greater than 0 is the common case in practice. F greater than 0, that means v greater than 0. Now, thing is that if this is the situation, f greater than 0, how we can make it exactly specified? Basically, there are two options. First option is we can specify more number of disturbance variables. So, by specifying more number of disturbance variables, if we can specify more number of disturbance variables, then number of unknown variables is reduced. Fine. So, this is one option, and in the second option, by incorporating more number of controller equations. This is the second option. Either we have to reduce the number of unknown variables, or we have to increase the number of equations to make the f equals 0. Anyway, we will discuss these degrees of freedom with taking one simple example. We will consider the stir tank heater to describe this degrees of freedom analysis. Stirrer tank heater example. For degrees of freedom analysis. So, before going to analyze the degrees of freedom, we need the model. So, first we will develop the model for this system, and then we will go for the degrees of freedom analysis. The schematic of this system we have to draw, we have to develop first. So, this is a phi and temperature is Ti. Now, steam is introduced here through the coil for heating purpose. This is steam. Suppose flow rate is Q. Outlet flow rate is F and temperature is T. Now, liquid in the tank has the height of H, temperature here also T, cross sectional area of this tank is A. Now, before going to develop the model, we need to consider some assumptions. Fine. So, what are these assumptions? First assumption is the tank is perfectly mixed. The tank is perfectly mixed. Assumption is rho and Cp both are constant. Third assumption is the tank is perfectly insulated. The tank is perfectly insulated. That means there is no heat loss from the tank to the surroundings. So, first we will develop the total mass balance equation. Total mass balance equation. Fine. So, what is the accumulation of mass? d dt, liquid height multiplied by cross sectional area, that is volume, volume multiplied by density, that is mass. H is the liquid height multiplied by cross sectional area, this is volume. Now, volume multiplied by density, that is mass. So, this is mass flow rate, I mean this is the rate of accumulation. What is the inflow rate? Fi rho minus F rho, this is the outflow rate. So, we can write this equation A dH dt equals to Fi minus F. This is the total mass balance equation. Since rho is constant, so we can get this from this equation. You give some equation number for this. Suppose this is equation number 1. In the next, you will go for energy balance. Fine. What is the accumulation term? Height multiplied by area, that is volume, volume multiplied by rho, mass, mass Cp, temperature difference is T minus suppose T reference. So, d dt of this is the accumulation term, H multiplied by rho, that is volume multiplied by rho, H multiplied by A, that is volume, multiplied by rho, that is mass. So, if this is the mass Cp and this is temperature difference. What is the energy input rate? Fi rho, this is mass flow rate, Cp Ti minus T reference, this is the energy input rate. What will be the energy output rate? F rho Cp T minus T reference. Fine. And another term is energy supplied by steam per unit time. Energy supplied by steam per unit time, that is Q. Basically, the unit of Q is here energy per unit time. Say for example, British thermal unit per minute, British thermal unit per minute. Yeah, the unit of this is energy per unit time. So, this is the energy added or energy supplied by steam per unit time. Now, if we simplify this considering T reference equals to 0, considering T reference equals to 0, and if we simplify the energy balance equation, we will get A H dt dt equals to Fi Ti minus T plus Q divided by rho Cp. This is the energy balance equation. If we consider T reference equals to 0 and if we simplify, finally we will get this energy balance equation. Fine. So, there are basically two equations, one is based on total mass balance and another one is based on energy balance. So, these two equations are, first one is A dH dt equals to Fi minus F, and this is Ah dt dt equals to Fi Ti minus T plus Q divided by rho Cp. You give some equation number to this, suppose this is equation number 2. So, this is the model structure. Fine. Now, we will go for the degrees of freedom analysis. How many variables are involved in this equation? H, Fi, F, T, Ti and Q. Fine. So, these are the variables. We can write V equals to 6. Agree or not? Agree. So, there are 6 unknown variables. Then how many equations are involved there? One is equation 1 and another one is equation 2. So, we can write E equals to 2. So, what is F? 6 minus 2, that is equals to 4. So, degrees of freedom for the example system is 4. We have discussed there are 2 ways to reduce the degrees of freedom. First option is we can specify some load variables. Fine. What are the load variables in this system? One is Fi, another load variable is Ti. So, if we can specify these 2 load variables, then the degrees of freedom reduces to 4 minus 2, that is 2. Initially it was 4. Now, 2 load variables we are specifying. How we can specify? By the direct measurement. We can measure this flow rate, we can measure this temperature, then we can get the information of flow rate and temperature. That means Fi and Ti are known. That means degrees of freedom, we can write 4 minus 2, that is 2. Another option I told, by including some control equations. For the example liquid heating tank system, what are the controlled variable and manipulated variable pairs to be considered? One is height, another one is temperature. Fine. So, we can manipulate this height, we can control this height by the manipulation of, suppose F, we can control this temperature by the manipulation of Q. So, we can develop 2 control equations. Although we did not study the control equations, I am just mentioning the simplest control equations for these 2 control pairs. If F is the manipulated variable, the control equation we can write like this: F equals to Fs plus Kcf multiplied by Hd minus H. Fs is the steady state value of F. This is the steady state value of F. Kcf is one tuning parameter, which the values of that tuning parameter we need to determine, that is constant Kcf basically. Hd is the desired value and H is the liquid height. So, this is one additional equation. Similarly, if we consider another control scheme for temperature, in which Q is the manipulated variable, we can add another equation, Q equals to Qs plus Kcq Td minus T. Fine. Here Qs is the steady state value of Q, Kcq is the controller tuning parameter, that is a constant term, then this is desired temperature. Fine. So, additionally we are getting 2 equations. We had F equals to 2. Now, if we can add 2 equations, then the degrees of freedom becomes 0. Got the point? So, we had basically degrees of freedom 4. Additionally, we have specified 2 variables, load variables through direct measurement. Then we have just paired controlled variable, manipulated variable. Then we got two additional control equations, and finally the degrees of freedom becomes 0. That means the system is exactly specified. Fine. Thank you.